Hey everybody, welcome back. This is Gunnar again from Austin Capital Data, and we will be continuing our discussion about the foundations of AI this month and trying to get everybody up to speed and interested in this idea, this revolutionary idea. We can start from the beginning with a really maybe audacious idea that took root in the 40s and 50s. It starts with the idea that perhaps we could use computers to model human thought. And we get to some kind of strange ideas that look maybe a little bit like, so what is that? And what are we trying to get? Maybe a cyber neuron? A computer version of a neuron? Well, you might start thinking about that, and how do you actually get that to work? Mccollogh and Pitts in 1943 came up with this idea and started to model this. So left over here, there's inputs. Those inputs are summated over here, and then they lead to a gated function, a step function. Most importantly, those inputs, there's multiple inputs into each of these things, and there are weights. So you can see the weights there as the W's. That's the basic idea of an artificial neuron, that you have this very simple function. Now, it doesn't stop right there. Obviously, you can't do a whole lot except a binary output with this. But in 1958, Frank Rosenblatt was able to put this idea together and build something called the perceptron. And the idea behind the perceptron is that you could take many of those gates, many of those artificial neurons, and have an input over here. It looks like an X, right? So that would be the input for an X. It's an array that's representing exactly the X. If you move over here, we would code that into another array, and then there's a random connections into some sort of a matrix. What I want you to note there is that the matrix doesn't really look like the original X. It's actually just scrambled up based on how the neural net is built. And then finally, it leads to some outputs that are much more like classifications. So you can see those at the end. Those would be the classifications at the end. So maybe it would be three outputs, three different letters that you're trying to train this thing to recognize. That's the basic idea, and that's how we will conceptualize an artificial neuron and then a unit of computation, which is a perceptron. Now, in order to bring this to life, we have to think about some maybe more interesting use case. And the classic one is called the MNIST challenge. MNIST is 60,000 handwriting samples. You can see those up over here, right there, some examples of that. And basically they're handwritten digits that go from 0 to 9. Obviously these vary quite a bit. And the task is to train a neural net to understand which digit is which. So you'd see at the end there would be a call. This is probably a 0. This is probably a 1. What I want you to notice is that by training this on this very relatively simple data set, we're able to train variations. So you're basically saying all 9s, for example, that we have in the data set would fit into this certain space. And the inputs to here are 28 by 28 squares of black and white. So it's very easy to sort of map that onto a number of artificial neurons. You can see the idea of layers here. So this is what the MNIST challenge would look like when it's built into a neural net. So you can see this layer over here is actually going to represent the reflection of the letter on a matrix. Internally, we've got some downsampled matrix that's going to be an abstraction of it. You'll see that in the second layer. And then as we move over to the right-hand side, you can see this vector that's a single vector from 0 to 9. Now I'm going to do a little demo. The links are down below, but I'm going to go step through it so I can really talk through what exactly is happening. Okay? It's pretty exciting visual for this this use case. Just take a deeper look into this net. So the thing I want you to notice, again, is that there are layers here. The top layer is the full representation of a number, and then the lower layers are downsampled layers. So we can see each of these squares is something, is one of those virtual neurons, one of those cyber neurons, and they're arrayed in a way that allows us to get the fundamental characteristic of each of those numbers and then decode it. you can see the last layer there is just a simple line of numbers that you could have. Let me move that up, or maybe I'll move that down so you can see that better. Okay, so you see the numbers there, 0 through 9. So let's start to draw here. So for example, I'm going to draw a 7, and you can see immediately sees that it's a 7. We can also undo that. I can draw a 1, and immediately it sees that this is probably a 1. We're talking about probabilistic math over here. So based on this input, there's a high probability that this is a 1, and that's sort of the way you want to think about this. The other thing I want you to notice is as I draw them, the representation over here, much like Rosenblatt's representation, is no longer the representation that a human would see. So let's take 3. That's actually a harder one, and you can see as we populate it, it becomes a 3, but I think it's going to probably have a little bit of an issue, right? It bounces around a lot there. Okay. So to leave you, let me give you another video that I found that's pretty interesting. It's by a person named Dmitriov, and he did something very similar to what I just showed you, except made it a lot more artistic. All of these links are going to be in my bottom description, and I encourage you to take a look at them and enjoy them. So you see here the complexity of this perceptron. As the numbers change, the different artificial neurons light up and the probabilities change. Now this video goes through a number of these different types of architectures. We'll just run through one more where they have a multi-layered perceptron. So we'll see pretty soon this will turn into something with multiple layers. So this is the way we get different performance out of these neural nets, with different layering structures, different weighting structures. It's mostly the architecture that changes. All right. So without further ado, thanks for coming by. So I hope you got a lot out of that. There's a lot more to drill into. I'm just pointing to some of the resources and giving you some of the major ideas so you can really understand these for yourself. Next week we'll do this again, and I'll talk about how you encode something much more complicated than a handwritten number. How is something like a image encoded and decoded? Thanks.